Good morning. Today we will study the geometrical scalar triple product and its geometrical interpretation. So, in earlier videos we have studied how to perform the multiplication of two vectors. The multiplication of two vectors can be performed in two different ways. If the result of multiplication of two vectors works out to be a scalar quantity, it is called as scalar product or the dot product of two vectors. And if the result of multiplication of two vectors works out to be a vector quantity, it is called as the vector product or the cross product of two vectors. On the similar lines, if the result of multiplication of three vectors works out to be a scalar quantity, it is called as scalar triple product. And if the result of multiplication of three vectors works out to be a vector quantity, it is called as vector triple product. So, depending on how we take the multiplication of the three vectors, the result of multiplication of three vectors can be either a scalar quantity or a vector quantity, and depending on that we have the two types of triple product and one is the scalar triple product and the other is vector triple product. So let us first discuss this scalar triple product of the three vectors. For that purpose, let us consider we have the three vectors A bar, B bar and C bar. We have said that if we take the dot product of two vectors, the result is a scalar quantity, and if we evaluate the cross product of the two vectors, the result is a vector quantity. Now, for the product of three vectors to work out to be a scalar quantity, we can evaluate the product of these three vectors in such a way that if we take the dot product of the first vector A bar with the result of the cross product of the remaining two vectors B bar and C bar, then the result of multiplication of the three vectors will be a scalar quantity, and such product or such multiplication of the three vectors is called as scalar triple product. So, the scalar triple product of the three vectors then can be expressed as A bar dot B bar cross C bar, because this bracket results into a vector, and if we take the dot product of this vector with the vector A bar, the resultant quantity will be a scalar. So, this type of multiplication of the three vectors is called as scalar triple product. It is called as scalar triple product. This scalar triple product sometimes is also called as box product, and this box product is represented as A bar, B bar, C bar in the square bracket. If we represent the three vectors A bar, B bar and C bar in this square bracket, it means that this is the scalar triple product of the three given vectors A bar, B bar and C bar. And in notation, it is represented like this. Now, we can evaluate this scalar triple product let us consider that the cross product of b bar and c bar is a vector d bar. Let us consider, for the sake of simplicity, the cross product of b bar and c bar results into a vector d bar. And then if we take the dot product of a bar with d bar, this will be a scalar. It will result into a scalar quantity, and this is nothing but equal to a d cos theta. That we have said. A is the magnitude of a bar, d is the magnitude of d bar, which means to say that the magnitude of b bar plus c bar, and theta is the angle between a bar and b bar plus c bar. So this results into a scalar quantity. So this type of product is called as the scalar triple product of the vectors a bar, b bar and c bar. Now let us evaluate this scalar triple product of the three vectors in terms of the components of the three vectors, rectangular components of the three vectors. So let us evaluate the scalar triple product. Let a bar is expressed as I cap ax plus j cap ay plus k cap az. B bar is expressed as I cap bx plus j cap by plus k cap bz, and the vector c bar is expressed as I cap cx plus j cap cy plus k cap cz. In terms of the rectangular components, the three vectors can be expressed like this. And now, if we evaluate the scalar product of these three vectors, we can express it like this: a bar dot b bar plus c. So this is nothing but equal to a bar is expressed as I cap ax plus j cap ay plus k cap az dot, and the cross product of two vectors we have seen in earlier video that this cross product can be expressed in the form of a determinant. The first row of determinant is the unit vectors ijk. The second row of the determinant is the components of the first vector in the product, and the third row is the components of the second vector in the product. So this cross product b bar cross c bar can be expressed as a determinant. The first row of determinant is the unit vectors ijk. The second row is the components of the first vector in the product, and the third row is the components of the second vector in the product. So we can express this scalar product in terms of the components of the three vectors like this. And now, if we evaluate this product, here we have to take the dot product of each term in the first bracket with the each term in the second bracket, or if we solve this determinant, it will give three terms. So the first term will be I dot I. So I dot I is 1. So it is ax. Let us write I dot I also. So this is I dot I ax into bracket by I cap by cz minus bz cy. Then I dot j and I dot k will be 0. J dot I will be again 0 plus j dot j into a1 into bracket, it will be bxcz minus bzcx plus j dot k will be 0, k dot I and k dot j will be 0 and k dot k will be 1. So this is k dot k into az into bracket, it will be bxcy minus bycx. So here I dot I, j dot j and k dot k is 1. So we can express this as ax into bracket bycz minus bzcy plus ay into bracket bxcz minus bzcx plus az into bracket bxcy minus bycx, and this expression is nothing but the determinant of this expression is nothing but the determinant of ax, ay, az, bx, by, bz and cx, cy, cz. So the scalar product of the three vectors a bar, b bar and c bar is nothing but the determinant of the components of the three vectors in the product. So the first row is the components of the first vector, second row is the components of the second vector, and the third row is the components of the third vector in the product. So this is how we can evaluate the scalar product of the three given vectors a bar, b bar and c bar in terms of their rectangular components. If we evaluate the scalar product of the unit vectors, what will be the scalar product of the unit vectors? Suppose we have the unit vectors I, j and k. The scalar product of these three unit vectors can be expressed as I dot j cross k. What is j cross k? J cross k is I cap. So this is nothing but equal to I dot I cap dot I cap, and as we know well that I cap dot I cap is 1. So the scalar product of these three unit vectors I, j, k works out to be equal to unity. Similarly, if we rotate these three unit vectors in cyclic order, the other combinations for the scalar product of these three vectors can be expressed as j dot k cross I. So again this is equal to j dot j and this is equal to 1, as well as k dot I cross j is nothing but equal to k cross k and this is equal to 1. So we observe that the scalar product of the unit vectors works out to be equal to unity. So that is the most important point that you must remember, that the scalar product of the unit vectors is unity. Now the next point that we must remember here is that if all the three vectors are coplanar, what will happen? If the three vectors are coplanar. What will happen? All the three vectors A bar, B bar and C bar, if lie in the same plane, suppose this is one plane that contains all the three vectors A bar, B bar and C bar. Suppose this is the vector A bar, this is vector B bar and this is the vector C bar. Now, if we want to evaluate the scalar product of such three vectors which lie in the same plane, then let us consider this scalar product is expressed as A bar dot B bar cross C bar. Now, first if we evaluate the cross product of B bar and C bar, this cross product of B bar and C bar will be perpendicular to the plane containing these three vectors A bar, B bar and C bar. So this will be B bar cross C bar. And now if we evaluate the dot product of A bar with B bar cross C bar, what we will observe here is that the vector A bar and B bar cross C bar are found to be mutually perpendicular to each other. And if we have the two vectors which are mutually perpendicular to each other, the dot product of such two vectors works out to be equal to 0. Because A bar is perpendicular to B bar cross C bar. Since A bar is perpendicular to B bar cross C bar, since A bar is perpendicular to B bar cross C bar, the dot product of such two vectors will be equal to 0. So, what we can conclude here is that if the three given vectors are coplanar, then the scalar triple product of such three vectors works out to be equal to 0. So, that is the most important point that we must remember in case of the scalar. Then the next point is, out of these three vectors A bar, B bar and C bar, if the two vectors are equal, out of the three vectors, if two vectors are equal, what will happen? If two vectors are equal. So for the sake of simplicity, consider that the vectors A bar and B bar are equal. So if we consider that A bar and B bar are equal, the scalar product of A bar, B bar and C bar then will become A bar dot A bar cross C bar, because A bar is equal to B bar. Here B bar is replaced by A bar. So now if we evaluate this dot product, this vector A bar cross C bar will be perpendicular to the plane of A bar and C bar. The vector A bar cross C bar will be perpendicular to the plane of A bar and C bar, such that now if we take the dot product of A bar with this vector A bar cross C bar, these two vectors are once again perpendicular to each other, and when these two vectors are perpendicular to each other, their dot product will work out to be equal to 0. So, out of the three vectors, if any two are equal, then it is observed that the scalar product of such vectors works out to be equal to 0. So, there is another property of the law of Lec on this scalar product. Then the next property of the law obeyed by this scalar product is that if the cyclic order of the vectors is maintained, if we maintain the cyclic order, if the cyclic order of the vectors is maintained, we can change the positions of dot and cross in the scalar triangle. If we have three vectors a bar, b bar and c bar, the scalar product of such three vectors is expressed like this, say a bar dot b bar or c bar. Now, if the order of these vectors is maintained, if the order of the vectors is maintained, then we can interchange the positions of dot and cross, so that the same scalar product of these three vectors can as well be expressed as a bar cross b bar dot c bar. The dot scalar product of such three vectors can as well be expressed as a bar cross b bar dot c bar. Here the order of the vectors is maintained, but on the left we have dot in this position, cross in this position. To the right we have cross in this position and dot in this position. So here we have interchanged the positions of dot and cross, and even if we interchange the positions of dot and cross by maintaining the order of the vectors, the scalar product works out to be one and the same. So that is another law proved by the scalar product. Then what will happen if we change the cyclic order of the vectors? If the cyclic order of the vectors is changed, then the sign of the scalar product gets inverted. Means if it was positive, it will become negative. If it was negative, it will become positive. So we can express this as a bar dot b bar cross c bar is equal to minus of a bar dot c bar cross b bar. So here what we observe is that the order of the vectors in the parenthesis is reversed. So whenever the order of the vectors is reversed, is not maintained, then the sign of the scalar product gets reversed, or it changes from plus to minus or from minus to plus. So that is how we can express the scalar product of the three vectors. Then if the cyclic order of the vectors is maintained, then the scalar product of the three vectors can as well be expressed as a bar dot b bar cross c bar is equal to b bar dot c bar cross a bar is equal to c bar dot a bar cross b bar. So if the cyclic order of the vectors is maintained, then what happens is that the scalar product a bar dot b bar cross c bar, or b bar dot c bar cross a bar, or c bar dot a bar cross b bar, all these three scalar products works out to be C. So these are the laws that are obeyed while evaluating the spherical product of the three vectors. So that is about the spherical product. In the next video, we shall study the geometrical interpretation of the scalar product.